want to take a moment to thank my most recent Patreon subscribers, Patrick, Michael, and Afshan. Thank you so much. Without you, this channel would not be possible. Please remember to like the video and subscribe and hit the notifications bell and comment. Thank you. Well, this is it. We have arrived at the point that we've been building toward for the last many weeks, which is the proof of the uniqueness of the real numbers. Now, this is something that Rudin does not prove, and indeed, what we're about to do is not anywhere on YouTube as far as I can tell. So this is a good thing to be able to do. And in addition, this is a really interesting exercise because in order to prove that, what this means is that there is only one set of numbers that satisfies, that is an ordered field with the least upper bound property. That any two such sets are going to be isomorphic and indeed the same set. So the way this is done is very interesting, and we'll learn along the way a whole lot about numbers generally, because in order to do this, the way we do it is sort of like nailing down a carpet or something. We're going to start by showing that the natural numbers are isomorphic. In other words, so what we're going to do is we're going to start with assuming that we have two sets, x and y, which both satisfy these criteria. So both x and y are ordered sets with the least upper bound property. So what we're going to show is that there's an isomorphism between them. So the way we do that is we start with just the natural numbers, and we sort of like tack down the numbers just along the natural numbers and show that there's a correspondence between the natural numbers in x and the natural numbers in y. Then we add the integers to that, and then we're going to start dividing these and show that the rational numbers are isomorphic as well. And then finally, once we have all the rational numbers laid out, we'll show that indeed all of the real numbers are isomorphic. So in order to do that, it's very interesting because in order to make this proof, we're going to have to explore what each one of these number sets really is. So what are the natural numbers? What are the integers and the rational numbers before we get to the real numbers, which of course is what we've been looking at for so long. And one really interesting thing that we're going to discover is that integers and rational numbers are almost exactly the same thing, which you may have heard. It's a common proof in math to show that there are countably many rational numbers. And what we'll discover is that that's at least partly because they're defined in almost exactly the same way, but one is sort of using addition and the other is using multiplication, which is also something we've talked about before. So we're going to learn a lot in the process of doing this, and I think it's worthwhile to do for that reason. And then what we'll end up with is showing that you cannot come up with two different ordered fields with the least upper bound property. They're going to be isomorphic, and the proof has two large parts to it. First we're going to show that there is an isomorphism between the two. Then we're going to show that indeed there's only one isomorphism, because it's possible, if you remember way back when we were talking about groups, if you have a triangle, you can rotate this triangle and you end up with it's the same group. You just identified each number with a different number, but then the orders or the operations on this triangle are going to be exactly the same. It doesn't matter which one you start with. This is an isomorphism, but we're going to show that in fact the real numbers are even more rigid than that. They can't even be, sort of quote rotated in this way or anything. They can't be rearranged in any way. There's only one way of arranging the real numbers. So all that's fascinating. And that's what we're going to get to in the next 4 or 5 videos. And each one I think is interesting for different ways. How the natural numbers are made, how the integers are made, the rational numbers, and then the real numbers. So to do that, the first thing that we need to do, that I need to do before we go any further, is define what an isomorphism is and a couple of other things. So an isomorphism, basically, in just using regular words, it means that the two are basically the same. Technically, what that means is that everything that makes X the structure that we're talking about is also true in Y. So what are our properties of X? It's that they have the addition axioms, the multiplication axioms, the ordering properties, and the least upper bound properties. So we have to show that so what an isomorphism is a map that goes from the numbers in one to the numbers in the other in a way that preserves those structures. So before I define what an isomorphism is more technically, first I need to define what a bijection is, because isomorphisms are bijections. And that's part of what we have to show, is that they're a bijection before we show the operations. Bijections, which means that the function is well defined, it's an injection, and it's a surjection. Now, I don't find these words very natural, but injection, the other way that people talk about injection is one-to-one, and the other way that people talk about surjection is that it's on two. So you can say that a bijection is a well-defined function that is one-to-one and on two. So what does all that mean? So well-defined means that the function gives a unique, unambiguous value for each input. In other words, it passes the vertical line test. So what that means is that if you had a function that went like this, that's not a function, because for any given value on the x-axis, you could have two or more values of f of x, right? If this is x, then this would be f of x, this would be f of x, and this would be f of x. So you can't tell from the function, if you take the function of x, you can't tell what the value is. This is not well-defined. So a well-defined function means that it passes the vertical test. So any function where no vertical line crosses twice is well-defined. Okay, one-to-one, so that's well-defined. One-to-one means that if f of x equals f of y, then x equals y. This is the same as the horizontal line test. And this isn't true of all functions, but it basically means that the function only goes up or it only goes down. But it can go like this, but it's never going to go up and back down, so that there's only one value. So that if f of x equals f of y, then x has to equal y. There's no, because on this function here, you could have that f of x equals f of y, but x could be here and y could be here, right? So this function is not one-to-one. So one-to-one means that for each value of y, there's one value of x. Another way of saying this is that r being less than s implies that f of r is less than f of s. And you can see, by the way, we're in a whole different realm now already from what we've been doing before, because everything we've been doing has been very much abstract algebra up to this point. And now, of course, isomorphisms exist in abstract algebra too, but now we're doing this way more. This isomorphisms, it's a whole new thing that we haven't really used much before, and that's going to be what this whole proof is about. So that's one-to-one, the horizontal line test. And finally, onto means that the function from x to y, for every y in y, there exists an x in x such that f of x equals y. In other words, y is covered by the function. What that means is that it goes all the way from top to bottom. It means that for every value of y on the y-axis, there is some x that will give you that value of y. So no matter what y is, no matter how high or how low, there will be some x that that gets you, or I guess this way, some x that gets you that value. So an example of a function that's not onto is an exponential function. This function is even increasing, so it is 1 to 1 because it never buckles on itself, but it's not onto because there are no values of x that reach the negative values of y. Okay, that one's not onto. So a bijection is a function that is both 1 to 1 and onto. Okay, that's what a bijection is. So an isomorphism has to be a bijection. If it doesn't reach all the values of y, then it's obviously not going to be able to. It's not going to be a 1-to-1 correspondence from one to the other. So okay, what is an isomorphism? Okay, so as I already said, so we're going to have two systems satisfying the axioms for real numbers. So each have an addition operation, a multiplication operation, and an ordering operation. Point is, they're not the addition and the multiplication, they're not necessarily the same in these two systems. What we're going to show is that in fact they are, but right now they're not necessarily. So we're going to have to refer to them separately. So we can't just talk about plus. So plus in the x set will be plus sub x, and this will be plus sub y, and then times will be times x and times sub y, and then less than x and less than y. So we have to do that so we know which set we're doing the operation on. So an isomorphism between x and y is a bijection phi from x to y such that for all u and v in x, we have the following. So we use the letter phi for our isomorphism. Okay, so phi for me always represents an isomorphism. So one is that phi of u plus v equals phi of u plus phi of v. Two is that phi of u times v equals phi of u times phi of v. And three, if u is less than v, then phi of u is less than phi of v. So this means, in other words, that phi is additive. This means that phi is multiplicative, and this means that phi is order preserving. So you can see here, I'm putting the x here because u and v are in x, but phi of u is in y because we've taken the element of x and gotten out the appropriate element in y. So phi of u and phi of v are in y. So here we're using the y version of addition. So what we're showing is that if you add them first and then take phi, that's going to be the same number. You're going to end up at the same place as if you take phi of u and phi of v and then add them in y. And so you can basically think of this, it's like you can go either direction and get to the same place. So if we had u and v, and this is in x, we could either add them here and then take phi up to some number up here, or we could take u and v, do the phi first, and then add them together. Okay, so we're gonna end up in the same spot either time. Then same is true of multiplication, and then this says that if u is less than v in x, then phi of u is going to be less than phi of v in y. And then furthermore, it's easy to show that if these three things are true, then the inverse function, that if phi defines an isomorphism, then the inverse function will also define an isomorphism. In other words, going the other direction will also be an isomorphism. So when we say that the real numbers are unique, what we're saying is that any two systems that satisfy the axioms of real numbers are isomorphic. So there's always going to be a connection between them that you can define in this way. So the uniqueness theorem states if x and y are two systems satisfying the axioms of real numbers, then x and y are isomorphic. And let me say one more time that there's actually two parts to this. So the first thing we have to show is that we can define an isomorphism between x and y. But that's not the end of the proof, because we're saying more than that. We're saying furthermore that the real numbers are rigid. And what that means is that there's only one isomorphism between x and y, and that it sends the same number to the same number. So it's the identity. It's called the identity automorphism. So we'll talk more about that after we finish with the isomorphism. So what we have to do first is show that there is an isomorphism between any two sets that satisfy the axioms of real numbers. So for x and for y, there's several symbols that we'll use repeatedly. So 0, y, 1, y, plus y, times y, and these represent the 0 element, the 1 element, the plus operation, the or the times operation, and the less than operation in y. And then the same is true, of course, with x. So the important thing to remember from the axioms, we were able to prove that 0 is unique in a field, and that 1 is unique in a field, and also that 0 is less than 1. Those were consequences of the addition and multiplication axioms. So we're just referring to the additive identity, the multiplicative identity, and so on. So the proof. So the proof, as I said, it's going to go through 4 steps. First, we have to embed the natural numbers into x and y and show an isomorphism between the natural numbers. Then we do it for the integers, the rationals, and finally the reals. So the first interesting thing about this proof is that step by step, the first thing we have to do is understand what is this system that we're looking at. So what are the natural numbers? So we need to see how the natural numbers are constructed themselves, and then how do they fit into x and y? And then what is the isomorphism between them?
Okay, here is the link to the first video in this chapter. Here is the link to the previous video. Here is the link to the next video. And click here to subscribe, and please join me on Patreon. The link to that is below in the description. Thank you.